Hi everyone, this is Dr. Meena, Assistant Professor, Department of Physics, JJ College of Engineering and Technology, Tiruchirappalli. Here we discuss about the topic of quantum confinement and quantum structures, one of the most fabulous topic in nanotechnology. Before I starting this section, ask one question. Why do modern devices are continues to become smaller, faster and more energy efficient in every year? To think about a smartphone, a laptop, a smartwatch and QLED television, although the devices are becoming smallest and the performance continues to improve. In this lecture, we will explore nanomaterials and the dimensions, quantum confinement, differentiate between bulk materials and nanomaterials, quantum structures like quantum well, quantum wire, quantum start and practical applications. Introduction to nanomaterials. Why we study the nanomaterials? Small size, big difference. That is the matter of nanotechnology. In nanomaterials having least one dimension in 1 to 100 nanometers. The nanomaterials exhibit unique electrical, optical, magnetic and mechanical properties. The properties differ from significantly bulk materials, large volume, surface to volume ratio, quantum confined. For examples, gold particles, carbon nanotubes, quantum dots and nano wires. Bulk materials, differentiate between bulk materials versus nanomaterials. Bulk materials, imagine a playground. Here, electrons can move freely in all directions. The energy levels almost continuous. Then the band gap remains constant. For example, silicon chip, copper wire and iron rod. In nanomaterials, think about a playground become a tiny room. Electrons cannot move freely. Movement is restricted. This restricted is called as quantum confinement. Does quantum confinement occur? The quantum confinement occur when particle size less than or equal to exciton 4 radius, because electrons wave functions becomes confined, electrons energy levels becomes quantized, energy spacing increases, then optical and electrical properties become size dependent. Exciton and Bohr radius. Exciton, an electron hole pair bound together by Coulomb attraction. Exciton, Bohr radius, the average distance between electron and hole. The particle size less than exciton, Bohr radius. Effect of particle size. In bulk materials having continuous bands. For example, rainbow. In bulk materials, smallest band gap, lower energy emission and it emits red colors. In nanomaterials, discrete energy levels. In example, EM waves, electromagnetic waves. Then large band gap, higher energy emissions have in nanomaterials that emits blue color. Energy level diagram for bulk materials and nanomaterials. In bulk materials, no confinement. In quantum well, one dimension are confined. In quantum wire, 2 dimensions are confined. In quantum dots, 3 dimensions are confined. In bulk materials, continuous energy bands occur. Then the quantum well is discrete energy levels in one direction. Then the quantum wire is discrete energy levels in 2 directions. Quantum dot is discrete energy levels in 3 directions. Quantum confinement in nanostructures. Electrons confined in one direction, then electrons can easily move in 2 dimensions. It is called quantum well. Then electrons confined in 2 dimensions. Quantum wire, electrons can easily move in 1 direction. Classification of quantum structures. Structure of bulk materials, 3D bulk materials. Then quantum well is 1 dimension is confined. Then quantum wire is 2 dimension is confined. Quantum dot is 3 dimension is confined. Confinement direction is bulk materials have no confinement. Quantum well is confined in 1 dimension. Quantum wire is confined in 2 dimensions. Quantum dot is confined in 3 dimensions. Free movement of direction in bulk materials freely in all 3 dimensions. Quantum well is free in 2 dimensions. Quantum wire is free in 1 dimension. A quantum dot is free in 0 dimensions. Electron motion of bulk materials in 3 motion. Electron motion of quantum well is 2 dimension motion. Then quantum wire is 1 dimension motion. The quantum dot is no motion because quantized. The energy level of bulk materials continuous bands, and the quantum well is discrete energy levels in 1 direction. Quantum wire is discrete level in 2 directions, and the quantum dot is discrete level in 3 directions. Quantum well, electrons confined in 1 dimension and free to move in 2 dimensions. For example, gallium arsenide and semiconductor lasers. For application of quantum well, laser diodes, LED and optical modulators. Quantum wire, electrons are confined in 2 dimensions and move freely in 1 dimension. For example, silicon nano wires and carbon nanotubes. For applications, nano sensor, nano electronics, field effect transistors. In quantum dot, electrons are confined in all 3 dimensions. Properties of quantum dot: atom-like energy levels, strong fluorescence, size depend color emissions. Quantum dot applications for QLED displays, solar cells, biomedical imaging and quantum computing. Application of quantum confinement and quantum structures, QLED televisions, solar cells, biomedical imaging, quantum computing, laser diodes, photo detectors, optical communication and nano electronics. In QLED televisions, quantum dots emit highly pure red, green and blue light. In solar cells, quantum dots can absorb a broad range of sunlight. Quantum computing, quantum dots can function as qubits. Laser diodes, quantum confinement allows precious control of emission wavelength. Photo detectors, they are used in imaging systems, sensors and infrared detectors. Optical communication, quantum dot laser provide stable, high speed and low noise optical signals. Nano electronics, quantum confined structures enable the fabrication of nanoscale transistors, memory devices and single electron devices. For advantages, tunable band gap, low power consumption, battery electrical properties, high optical efficiency and high speed electronics. In summary, materials exhibit unique properties due to quantum confinement. Quantum confinement occurs when particle size approaches, then the exciton Bohr radius, band gap increases with decreasing energy levels. Quantum structures are classified into quantum well, quantum wire, quantum dot. These structures are widely used in modern optoelectronic devices. Thank you.